and think about the question that I have up on the slides and think to yourself about what you think that answer might be. Okay, so what do you guys think? This is from class on Monday. We talked about the SN2 mechanism of alkyl halides reacting. So which one of these answers best describe the rate law for an SN2 mechanism? All right, we got a lot of answers with B in the chat box, and that is indeed correct. And the reason for that, the reason that B is correct, is because for an SN2 mechanism, the number 2 stands for bimolecular, and in an SN2 reaction, both the alkyl halide and the nucleophile are coming together in the rate determining step. So the rate determining step, which is the step that gives the rate equation for an overall reaction, has both the alkyl halide and the nucleophile present as part of the rate determining step. So on your own, I want you to think for a second about this exact rate law that depends on the alkyl halide and the nucleophile, and think about what factors you might imagine impacting the rate and impacting how this reaction occurs, whether it's an easy reaction to do or a hard reaction to do. And we'll talk about this throughout sort of most of the class today. So, or part of the class today, I guess I should say. So don't have to answer this right now, but just be kind of thinking about this in the back of your mind on your own. All right, today we are going to be continuing with chapter 6. My hope is to get through or almost all the way through both types of nucleophilic substitution reactions so that on Friday we can finish up whatever we have left here and also talk briefly about a topic I skipped over, which is another reaction for synthesizing alkyl halides. Just a reminder to everybody, please include Chem 301, ideally with your section 003, in the subject line so that I can catch the emails from you guys. You guys are very important to me. Also, office hours are today via Zoom. You can find that link on your syllabus. I'm going to be having some office hours later this week, and I will make an announcement via Canvas as to when that will be. Okay, couple of announcements. First, I told you guys on Monday that I would tell you today how I was calculating the midterm grades. I am not going to talk about that right now because frankly, we don't have time for it. But when I post the slides later today, this block will be removed and you will be able to see in great detail how I calculated your midterm grades. And I'll field questions from them independently. Exam 2, as you guys know, and as has been kind of being chatted about in the chat box in the background, it is this coming Monday. So Monday of next week, March 28th. It's going to cover all of chapters 4 through 6. We will finish chapter 6 on Friday. It will be similar format to exam 1, where there's going to be, oh, shoot, you guys, this is a mistake on this slide. Obviously, you guys are not going to have a Scantron. I will fix this. This is a cut and paste error. Your exam will be delivered through Canvas and using the Respondus browser for part 1, which is multiple choice. So multiple choice on Respondus and free response separately. I'll fix that before posting. And then just a reminder, these are all the same resources that I reminded you guys about on Monday that you still have. My office hours, which are today, and then at some point later in this week, which I will post. You have another SI session with Honor tonight at 5 p.m. And tomorrow, I believe he might be doing a marathon session tomorrow. And then of course the CLC, the Campus Learning Center, has drop-in hours where there is literally a tutor specifically for this class just waiting and dying to answer your questions about this class every Monday through Friday and hours on Sunday. And you can find the hours at that link there. Okay, here is our chapter 6. Oh, Brittany, you have a question?
Yeah, so for the exam, is it gonna be like what you did last time, like where we have Sunday and Monday, or yes, you're just going to make us do it? Okay. I just wanted to make sure because that just says Monday. So I wanted to make sure.
Yeah, that's, if you look at the posted slides from this past Monday, those announcements are more accurate. I'll also fix these before I post them. Basically, there will be a window. There will be a window that will, excuse me, include all of Monday and either part of Sunday or part of Tuesday. I haven't decided yet. I was waiting to find out about honors marathon session and some other things. But the window will cover like a 36 hour period where you guys will have any time in that 36 hours. But Monday, the whole 24 hours of Monday will be part of that 36 hours.
Okay, I just wanted to make sure there was still going to be a window. Thank you.
Yep, there's a window. Okay, so here's chapter 6, and what I want to do today is try to get through both mechanisms of nucleophilic substitution. We got a good start on SN2 on Monday, so we're going to finish that up today. And my hope is to make it into a good portion of SN1 today as well. So let's go ahead and get started by reviewing where we were on Monday with SN2 reactions and the mechanistic implications of that reaction. So as you guys know, we've been talking about reactions of alkyl halides and specifically nucleophilic substitution, which can occur through either of these two mechanisms. A bimolecular mechanism, where both the nucleophile and the electrophile, in this case our alkyl halide is the electrophile, both our nucleophile and our electrophile are coming together in the rate determining step, which makes this a bimolecular reaction, or SN2. There's also an SN1 mechanism, which we'll talk about during the second portion of class today, where the rate determining step depends only on the alkyl halide, and the nucleophile doesn't come into play until after the rate determining step has already occurred. So for the beginning part of class today, I want to focus just on the top here with bimolecular nucleophilic substitution. And the first couple of slides are going to be review from previous. So here is the mechanism. I should say that I swapped out, and you guys might notice, I swapped out on the slides on Monday. This was a specific example with a specific nucleophile and a specific substrate. I wanted to make it more generic to help everybody kind of see things a little bit easier. So I changed it up and I've put the generic form of this reaction here. All right, so here it is again. And notice that in an SN2 mechanism, which is bimolecular, we have our nucleophile and our electrophile coming together, forming a new carbon nucleophile bond at the same time that we are breaking a carbon halogen bond. What this means is a couple of things. One is that we can call this a concerted reaction because the bonds being formed and the bonds being broken, those two activities are happening in concert with each other or at the same time. This means also that the reaction is second order overall because it has two different molecules involved in the rate determining step, one of the alkyl halide and one of the nucleophile. The other thing you can notice here, and this has very key important consequences for how this reaction occurs, our nucleophile has to come in and attack our electrophilic carbon from the backside opposite of where the carbon halogen bond is. Because of that constraint on how the nucleophile approaches the electrophilic carbon, our remaining three substituents that are sort of bystanders in this reaction, they, instead of being pointed towards the nucleophile, which is how they're oriented as the nucleophile approaches because of the tetrahedral geometry here, in the transition state, they're going to go through and flip through a planar intermediate that is perpendicular to your screen here, where they're all in this middle plane together. And then after your carbon halogen bond fully breaks and your carbon nucleophile bond is fully formed, those three substituents will be kind of pointed in the opposite direction than your new carbon nucleophile bond based on the constraints of a tetrahedral geometry. So we'll see this over the next couple of slides in different ways. But first I want to show you an energy diagram for the SN2 reaction. I showed you guys this on Monday also. The key features here are that there's only one mountain, right? We're going to go from some reactants directly to some products through a transition state that has partial bond formation and partial bond breakage. The levels, the energy levels of these reactants and products will depend on the specific reaction that we're talking about, but all SN2 reactions are going to fall into this general theme of having only one mountain peak. It's a concerted reaction, so there's only one step in the reaction. And that means there's only one transition state, which is the highest energy point along this curve. So back to those mechanistic or stereochemical considerations. We've already talked about, but I'm going to reiterate now, that the nucleophile in an SN2 reaction has to come in from the opposite side of the carbon-halogen bond. It has to come into the back side of that orbital that's holding the halogen. And that physical constraint or geometric constraint means that our nucleophile is going to come into a side of the molecule that has the 3 remaining substituents pointing towards it. But as that bond is being formed, those 3 substituents are getting pushed and flipped over the same way an umbrella would get turned inside out in a really bad rainstorm. They're pointed in one direction at the beginning, and then they go through a planar kind of transition state, and they flip over to be pointed the opposite way in the end. This is a concerted mechanism where this bond forming between our carbon nucleophile and the bond breaking between the carbon and the halogen, those things are happening at the same time. And that means that every time you do an SN2 substitution, that substitution occurs with inversion at the stereochemistry at the carbon center. Every single time you do an SN2, these substituents are going to flip inside out the way an umbrella would in a bad windstorm. Okay, so in this case up above, we can't really tell that difference because all 3 substituents are the same. But if all the substituents are different, if that electrophilic carbon in the center is a chiral carbon, then this feature has major consequences on the stereochemistry of the product. And we saw that in an example on Monday, where if you have a configuration that looks like this, with the ethyl group coming towards you, the methyl group going back, and hydrogen in the plane, but all 3 of those things kind of pointed towards the left, then when our nucleophile comes in, those 3 substituents are forced to flip over to the other side. Notice that the methyl group stays to the back. It just moves from the left through the back and to the right. The ethyl group stays to the front, and the CH group stays in the plane. So they're not changing the order of those 3 substituents. They are just flipping kind of inside out like an umbrella. But the thing that does change is the location of the carbon halogen bond versus the carbon nucleophile bond, because the carbon nucleophile bond will be formed kind of opposite to where the carbon halogen bond was. So this forced inversion of stereochemistry, which always occurs with an SN2 reaction, it always occurs with an SN2 reaction. This forced inversion of stereochemistry means that if you have stereochemical information contained in your starting material, that stereochemical information can be transferred to the product. Well, what do I mean by that? If, for example, you have 80% of the S enantiomer here instead of 100%, if you only have 80% S and 20% of this is R, every single molecule that was oriented S will be flipped, and in this particular example will become the opposite configuration. Likewise, every single molecule that was R will be flipped and become S in this particular equation. So I want to point out that it happens in this case, and it will in most cases, but not all cases, that when you do this flip, the S does become an R designation, but you have to be careful because if the numbers of the priority groups change when you change the nucleophile, the leaving group in the nucleophile, this S to R designation might not always hold true. We talked about that a little bit on Monday, so I'm not going to spend more time on it now. But if you're confused by what I just said, then come see me at office hours or ask at an SI session or at the Campus Learning Center drop-in hours. Okay, so everything we just talked about is stuff we talked about on Monday. I want to move on now to factors that affect the SN2 reaction. And I told you guys when we did that sort of quickie multiple choice question at the beginning of class to be thinking about that rate law and what that might mean for the factors that affect an SN2 reaction. So as you might imagine, the alkyl halide that's involved has a huge role to play in whether or not an SN2 reaction is likely to occur. So if you imagine mechanistically, that the SN2 reaction depends on the nucleophile and the electrophile coming together, then that means that the electrophile or the electrophilic carbon within your alkyl halide, the accessibility of that location will have a big impact on how well this reaction goes. If you have a less substituted alkyl halide, like a primary alkyl halide or even a methyl halide, that nucleophile is able to reach the electrophilic carbon more easily. And it's a little bit hard to see in our line and stick drawings here, but if we switch over to a space filling model, like I'm showing you up above, then it becomes really obvious that the methyl group is much bigger than the hydrogen group. And so as you keep on adding methyl groups or even bigger groups, it makes the area that that nucleophile has access to for this nucleophilic attack gets smaller and smaller the more groups you put on. So a primary alkyl halide, that's easy for an SN2 reaction. The nucleophile has the spot that it can reach to, and it will be able to do that reaction. As soon as you put even one more group on there, if you have a secondary carbon with two R groups coming off instead of just one R group coming off here, that space that your nucleophile has to access the electrophilic carbon is small. So it is possible to have that reaction work here. It does happen, it happens frequently, but it's a lot harder than if you have a primary alkyl halide. And importantly, very importantly, if you have substitution at all three of your positions on your alkyl halide, that is impossible for a nucleophile to attack. It is literally not allowed, as in not allowed, as in not going to happen. So let's take another look at this in a different way. So we can talk about this as how well the reaction is going to go. We can also talk about it as relative rates. And you can see that for SN2, the rate of a completely unsubstituted methyl halide is faster than the rate of a primary alkyl halide, which is faster than the rate of a secondary alkyl halide. And all of these are way faster than a tertiary alkyl halide, which literally is so slow that it can be considered as does not react using this mechanism because of those sterics. This chart is a chart out of your book just to give sort of a quantitative feel to what we've been talking about qualitatively. So I want you guys to look at this row right here on the chart for the secondary alkyl bromide right here. It's an isopropyl bromide, right? So it's a secondary carbon right here. It has two C groups or R groups coming off of it. That makes it a secondary carbon. That makes this a secondary halide. If we set that to be kind of our benchmark with a relative rate of 1, then we can do some comparisons here. If we compare our secondary halide to a primary halide, so we're just swapping out one methyl group for hydrogen, we can get this reaction to go 50 times faster. So our primary halide is much better at this reaction than our secondary halide. If we go the opposite direction and pop another methyl group on, then our rate becomes 1,000 times, actually more than 1,000 times slower by just putting on that tertiary, making that a tertiary alkyl halide. So you can see the sort of the dramatic difference here. You can also see if we go from this primary alkyl halide to a methyl halide, that's a pretty significant increase in rate as well. So those are the big ticket versions of this rate equation, but you can also see it in more subtle ways. So I want you guys now to compare the second entry, which is an ethyl bromide, a primary alkyl halide that has 2 carbons on it, with this entry down here, which is also a primary alkyl halide, right? The carbon where the halogen is attached only has one other R group. But in this case, it's a 4 carbon long alkyl halide, right? And so you can see having those extra 2 carbons in this structure means that that branch is kind of, as it's rotating around in space, is creating some steric hindrance for the nucleophile. And so this butyl bromide is about a little less than half the rate of this ethyl bromide. So if you compare the relatives right here, the ethyl bromide is about twice as fast, about 2.5 times as fast. You guys can take a look at this chart kind of on your own and look for more trends. But the big trends to know are the ones based on rough sterics, that methyl halides will always be faster than primary, which will be faster than secondary, and that tertiary halides are not valid substrates for an SN2 mechanism. Okay, the next thing that we need to think about, I told you guys to think about that rate equation, right? So in our rate determining step, our rate is dependent on the nucleophile and on the alkyl halide. So we just talked about some structural features of the alkyl halide that would impact how well this reaction goes for an SN2 mechanism, namely the sterics around that electrophilic carbon. But it's a bimolecular, right? It's an SN2 reaction, so it's a bimolecular rate law, which means our nucleophile and the strength of our nucleophile also plays a part in how well the reaction goes. And as you can imagine, stronger nucleophiles react faster. So this is a moment in time that we need to take a pause and take some time to talk about the difference between bases and nucleophiles, since they have a lot of the same features of having a high buildup of negative charge density. Before I do that, I want to just put up this chart. This is a chart from your book that lists out some common nucleophiles in order of their strength. And you can see that there's a lot of different things on this chart, and it might seem overwhelming at first. You might feel like, oh my gosh, how am I going to remember this? And the cool part about organic chemistry is you don't need to remember it. You do not need to memorize this chart. Please do not memorize this chart. If you memorize this chart, that is valuable brain space and memory space that should be dedicated to other things. Instead, what I'd like for you guys to do is use your fundamental knowledge from chapters 1 and 2 to think about nucleophilic strength from first principles. And just a reminder that as energy goes up, you have compounds that are higher in energy will be more reactive and less stable. Compounds that are lower in energy will be less reactive and more stable. So this little chart schematic that I have in the top right corner is a very generic tool that applies to all sorts of different things. And indeed, we can also apply it to nucleophiles here. Nucleophiles are going to be more nucleophilic. A compound will be more nucleophilic if it is less stable at carrying that negative charge or carrying that charge density or charge buildup. Okay, so I told you we need to take a moment to really drill down to the difference between basicity and nucleophilicity. So I want to take the time to do that now. This is important for this chapter, but will be very important for chapter 7. So we'll revisit it then, but for right now, it's still a feature that we need to be thinking about and knowing about. When we talk about basicity, we're talking about the capability of a compound to abstract a proton, so just H plus, from a nearby compound, right? And so in this generic form here, the electrons go with A so that you get A minus, and the proton transfers over to the base. So a strong base will be a highly reactive base, will be not happy about having to carry around the charge density or the charge buildup, the negative charge buildup that it has. It will not be stabilizing that negative charge, and it will want to grab that proton to try to quench that negative charge, right? A strong base will have a KEQ that favors the product directions, and that should make sense. Nucleophilicity, even though our compound in question here has a lot of similar characteristics and similar properties of having a rather large buildup of negative charge, nucleophilicity is not about how good something is at deprotonating something else, but rather about how good it is at reaching in and attacking an electrophilic carbon atom. And in this example, we're using actually an SN2 type of a reaction to define this. So the big font down here says in words what I've been talking about, but I want everyone to take a moment and look at the kind of italicized font here and note that this note here, basicity is inversely related to the acidity of the protonated species. Well, that might not make sense to you at first. It's a lot of big words strung together, but it is something straightforward, and it's something you guys already know from chapter 4, which is just to say a different way of saying the same thing. Strong acids have weak conjugate bases and vice versa, right? Weak acids have strong conjugate bases. Nucleophilicity, on the other hand, has nothing to do with proton transfer or proton movement. And so what that means is that in nucleophilicity, you could have a situation where you have the conjugate base of a strong acid, and that conjugate base might actually be a weak nucleophile, or it could be a strong nucleophile, right? So if you have the conjugate base of a strong acid, it would be a weak base. But if you have the conjugate base of a strong acid, it could be a weak nucleophile or it could be a strong nucleophile. And we'll see some examples of that as we go. Before we get to those sorts of examples, I want to talk about the trends in nucleophilicity. So remember back here, I told you I do not want you guys to memorize this chart. I instead want you to think about fundamental principles. And so I'm going to try to use those fundamental principles to point out a few trends that you guys can remember. And I do want you to remember these trends. So the first trend is that negatively charged nucleophiles are going to be stronger than their neutral counterparts. So that's the trend written out down below, and I've given you some examples up above. And one thing that I will say is that I will only ever ask you about pairwise comparisons, right? Which of these two things is a stronger nucleophile? And I will only ask you apples to apples comparisons. So both of these are nitrogen nucleophiles, and they're analogous to each other, except that one is negatively charged and one is neutral. The negatively charged one has been deprotonated. So in every case here, the negatively charged compound is a stronger nucleophile. And that should make sense to you based on the kind of the generic scheme we had. A negative charge is going to be a less stable species than the neutral species. So the negatively charged one will be a stronger nucleophile. Another trend that we can talk about is based on electronegativity, that nucleophilicity decreases as you move from left to right in the periodic table. This should make sense to you also. I'm going to use this example on the right here to talk about this. Fluorine is the most electronegative element. So if you have F minus, that fluorine is going to be the best at stabilizing that negative charge. It'll be better than oxygen at stabilizing that negative charge. And likewise, oxygen will be better than nitrogen at stabilizing that negative charge. So what is a more stable negative charge or a more stable compound is a less reactive compound. So the better the electronegativity is, the worse a nucleophile is. And our third trend here is a trend that increases with nucleophilicity as it goes down the periodic table. This does not have to do with electronegativity. Instead, it has to do with the size of your nucleophile and the polarizability of the electron cloud. So I'll explain what I mean by that polarizability on the next slide. But basically what I'm talking about here is that as you go down the periodic table, so iodine, which is at the bottom of the periodic table, it's going to have a larger electron cloud, and that larger electron cloud gives it more flexibility to reach the electrophilic center. And here are some pictures that kind of help explain that. I am not going to spend a lot of time in this class talking about hard versus soft, but that is a concept and a theory that you'll see in other classes in chemistry. But I want you to think about these things. They kind of are what they sound like. So a hard compound is going to be like a marble. You can't move it around very much. The electron cloud doesn't move around a whole lot. It's kind of set where it is and can't be moved around a lot. A soft electron cloud or valence shell is going to be like a marshmallow. It's going to be squishy, it's going to be big, and you can manipulate it to kind of reshape it how you need to reshape it to get the job done. So if you have a small valence shell, that nucleophile, as it's going to approach the sterically crowded electrophilic carbon center, it's going to have to distort its electron cloud to be able to reach over to the back lobe of the bond holding that carbon halogen. And because it's a hard nucleophile, it's not going to be very good at distorting its cloud. So it'll distort it a little bit, but it won't have great overlap here. Whereas if you have a big marshmallow cloud of electrons that need to get in and attack an electrophilic carbon center, that big marshmallow cloud has a lot more flexibility. The technical term I prefer is squishier. So this iodine, this I minus, is squishier, and it can take its electron cloud and move it and be able to reach over and get better overlap with that orbital that will help to break that carbon halogen bond. Okay, so this is what I mean by this bottom trend on the last page, that nucleophilicity increases as the size increases because there's a polarizability increase with size. That's covered by these pictures here. So I'm coming back to where we were just a couple of slides ago with this chart. And now we can begin to see we don't have to memorize this chart because we can look and compare things on the chart. If we look at I minus versus Cl minus, we know that I minus is bigger, and so it's going to be a stronger nucleophile because of that polarizability. If we compare OR minus with ORH, so if we compare an alcohol, ROH, with the deprotonated alcohol, we know that that deprotonated alcohol will be more reactive because it is less stable, because it is a negatively charged species as compared to a neutral species. So RO minus, just like HO minus, those are going to be better nucleophiles than their neutral counterparts. So we can see the trends that we just talked about being borne out in this chart. The other thing that I want to point out here is that I minus gives us a great example of a compound that is a strong nucleophile, but a terrible base, right? So you guys know that HI is a strong acid. If HI is a strong acid, then I minus should be a weak base, and it is indeed. So I minus is a weak base, but because of its large size and its polarizability, I minus is a strong nucleophile. So that's an example of a case where not all strong nucleophiles are basic. All right, someone has asked in the chat box, how come chloride is moderate? And so chloride is moderate because it's better than fluorine because it's a bigger electron cloud than fluorine, so it can move around and squish better to get to the nucleophile. But it's also, chlorine is a highly electronegative element, right? So because it is electronegative, it is capable of stabilizing that negative charge. The same thing with this carboxylic acid. We can draw a resonance structure for this carboxylic acid to show that that negative charge is stabilized because of the resonance structure. So the electronegativity in the case of chlorine minus and the resonance stabilization in the case of RCOO minus, those are what make them moderate nucleophiles as opposed to strong nucleophiles. Did that answer your question? Okay. So moving on, I wanted to put up this chart, which is also from your book, and just point out to you guys that with learning these SN2 reactions, or really in general learning nucleophilic substitution reactions, we can take an alkyl halide now and we can react it with all sorts of different nucleophiles, So check this out. In this one class, well, two classes on Monday and today, now we know how to make alcohols, we know how to make ethers, we know how to make all of these different types of functional groups. Because if you combine an alkyl halide with a nucleophile, we can displace that halogen with the nucleophile. And there are a lot of different options and available nucleophiles for us to choose from. So we just kind of dramatically increased our capabilities to do synthesis, to synthesize useful products. We'll talk more about that as the class goes on. Okay, time for a brain activity. So here's a question for you guys. Given what we just talked about, take a moment, a quick moment, because we have a lot to cover today, and think to yourself about which of these things is the strongest nucleophile. Okay, when you think you know the answer, you can put it in the chat box or shout it out. Okay, we got lots of C's and D's. This is exactly what I expected. A lot of different answers, C's and D's. The correct answer is C. The correct answer is C. So hopefully everybody found it pretty easy to rule out these top two because they are the neutral versions of the negatively charged species down below. So that gets rid of A and B. So we need to now decide between C and D. And the way we do this is to take a look at the stabilization and remember that a more stabilized negative charge is going to be less reactive. So we can take our carboxylic acid that's in D, we can draw a resonance structure where that negative charge is placed on either oxygen. That stabilizes this nucleophile in D, which makes it less reactive than the nucleophile in C, which again is the same electronegative element, an oxygen carrying that negative charge, but in case of C, that negative charge cannot be shared on multiple atoms. It's stuck on the oxygen where it is. So that means that C is the answer here. Someone's asked in the chat box, so a stable molecule is a weaker nucleophile. And that's right, and that's based on this chart that I said is generic for no matter whether we're looking for a nucleophile or whatever we're looking for. As energy goes up, you always get more reactive and less stable compounds, and the less reactive are more stable compounds. So if you have a more stabilized negative charge, like in the case of RCOO-, that is going to be a less reactive nucleophile than in the case of RO-, which is going to be less stable and therefore more reactive. And so you can use this kind of a chart to keep track of that. Okay, moving on, I'm going to use the rest of class time today to cover SN1 reactions, and we'll get as far as we can, and we'll just see where we go from there. Whatever we don't get to today, we'll finish up on Friday. Okay, we've been talking about the SN2 mechanism, which is a bimolecular nucleophilic substitution. We're going to switch gears now and talk about SN1 as a mechanism, which is unimolecular in the rate determining step. I'll show you this carefully over the next couple of slides. All right, here's the same kind of generic reaction I'm showing you down below. This is a unimolecular reaction. That's what gives it its name, SN1, for substitution of the nucleophilic variety and 1 for unimolecular. Only one species is involved in the rate determining step. So here is your rate law. Your rate law has a rate constant times an alkyl halide concentration. So this molecule is the only thing that impacts the rate here. In an SN1 reaction, that carbon halogen bond breaks, and what we get is a carbocation intermediate here. So when the CX bond breaks, the electrons are going to leave with that halogen, leaving behind a carbocation. And if you remember from chapter 4, I think, carbocations are planar, they're trigonal planar geometry. They have an empty p orbital that's going to have a lobe sticking out on either side. So because they're trigonal planar, we have an automatic plane of symmetry here. It's the plane that these three substituents are in. Well, what just happened then? We lost our stereochemical information. If we had a stereochemical center here, that is no longer a stereochemical center. It is now a planar carbocation intermediate, and our nucleophile has no way of deciding whether it should attack on the p orbital lobe that goes off to the right or the p orbital lobe that goes off to the left. And indeed, it happens in both ways in a statistical fashion, giving you a mix of the two compounds. This means that racemization occurs during this process in an SN1 reaction. And what I mean by that is that if we started out with stereochemically pure material, in the end, we're going to end up with 50% of one enantiomer and 50% of the other enantiomer, which is a racemic mixture. So the process overall can be considered a racemization. In the case where the nucleophile comes in from the right, as we have it drawn here, we get inversion of stereochemistry at relative to our original molecule. If the nucleophile comes in from the same side as where the leaving group used to be, then we get retention of stereochemistry at that chiral center. So both of these processes are occurring in about a 50-50 mixture, and so we get that racemization. Okay, so mechanistically, if we talk about the mechanisms and the curved arrow notation that shows where the electrons are going, I just want to take a couple of moments to go through this. These pink arrows are exactly the same curved arrows that I've had you guys draw before, and they're the same types of curved arrows that you might, for example, be asked to use to show the mechanism on exam 2 in the free response section. The arrows are always going from high electron density and showing where electrons start at the beginning of arrow and where they end up at the end of the arrow. So in the first step, the electrons in that carbon-halogen bond are going to be, the bond is going to be broken, and both of those electrons, this is a double-headed arrow, are going to go with the halogen, giving it an extra lone pair and leaving behind a carbocation. In the second step, that carbocation, which is a very strong electrophile, gets attacked by a nucleophile. 2 electrons from the nucleophile, whether they're from a lone pair or from some other portion of the molecule, 2 electrons from the nucleophile reach over to that carbocation and make a new sigma bond there. We have a possible third step, which we need to account for any protons that we need to take care of, and I'll show you guys in more detail what I mean by that. So these arrows represent the flow of electrons, and I'm going to go through each step a little bit more explicitly now and make sure we're thinking about all the considerations we need to. So here's in an example problem, step 1 of an SN1 reaction. First, we're going to form a carbocation. This is, of course, the rate determining step. The arrows for this reaction show that carbon-halogen bond breaking with the electrons of the bond going with the halogen and leaving behind this carbocation. So a couple of things to note here. In order for this to happen, this carbocation that you're creating must be a more stable kind of carbocation. We have to be able to create this carbocation, and if this was a highly reactive carbocation, we wouldn't be able to do this. The other thing that I want to point out is that this is actually a reversible reaction, right? You have a positively charged carbocation right next to a negatively charged, could be nucleophile, and indeed it can go and reform the bond that it just formed. Just think for a second, if this had been a chiral center and this bond was broken and then this iodide came back and reformed that center, would you regain the same chirality? No, you wouldn't, because this carbocation is planar. So after you've broken this bond, that iodide could add from either side, and that chiral center would be racemized. Okay, because this rate determining step, which is this first step of the mechanism, involves only the substrate, that's what makes this a unimolecular reaction. And we've seen that played out in both the rate law and the stereochemistry, meaning the scrambling of stereochemistry that we've seen. You guys might be asking yourself, well, why would this bond just break? Like, usually you're thinking about a molecule as being a molecule and it's just sitting around doing nothing. And when you have a reaction, you usually have to have a reagent to make that reaction go. So in the SN1 case, the reagents for this reaction are often just heat, which you'll sometimes see demonstrated as a triangle like this over the arrows, or written out as the word heat, and a weak nucleophile. So you can have a strong nucleophile in this case also, but you don't need a strong nucleophile because this carbocation is so reactive and so strongly electrophilic. But you can use any weak nucleophile, and so that means that sometimes you can even use a solvent to be the nucleophile. And so we'll see that example on the next page in step 2. Here's our same carbocation as from step 1. I've just carried it over to this slide. And in this case, suppose we were doing this reaction in methanol. The methanol has a nucleophilic site on it. The lone pairs of these oxygen are nucleophilic. And so even though methanol is not a very good nucleophile, it's a good enough nucleophile to attack a carbocation, because carbocations our reactive species. When we do that, we're going to create a new bond between our carbocation and our lone pair of electrons. So you can see the arrow again is showing what's happening with the electrons. They're moving from here, a lone pair on the oxygen, to become a new bond with that carbon atom that used to hold the carbocation. I want to take a moment and point out that it is really important that we start keeping track, and we make sure to keep track always of all of our electrons, protons, and formal charges. And this will be something that is helpful for you guys as you're going through problems to make sure that you didn't make a mistake. So if we look on the left-hand side here, we can't create or destroy charge, right? Charge is conserved and it has to be conserved. So if we started out with something that's positively charged plus something that's neutral, our overall side of this equation has a +1 charge to it. That means that we have to end up with a product that has a +1 charge to it also. And so we've done that here so we can see that we didn't make any mistakes. Okay, in this example, we also have to take care of a third step because this protonated species is not our product. Our product is going to be a neutral species. And so in our third step of this mechanism is to deprotonate our intermediate here. And we can use another molecule of solvent for that. And so here you can see the curved arrow notation showing the lone pair on the methanol, abstracting this proton. In this case, that methanol is acting as a base. That'll break that oxygen-hydrogen bond, and that electron shows this arrow shows the 2 electrons going back to become a lone pair on the oxygen. And so you can see that lone pair here in the product. So now we've completed this reaction. We've got ourselves a neutral product and also a protonated methanol for conservation of charge. This step is necessary if you end up with a nucleophile that is neutral, because if you have a neutral nucleophile, you'll end up having to deprotonate your product in the end. Okay, so that was the 3 mechanistic steps kind of written out in explicit detail. I want to also show you guys the energy diagram for an SN1 reaction, and make sure that you guys take the time on your own to compare and contrast this energy diagram with that of an SN2 reaction. So in an SN1 reaction, excuse me, there are more than one mountain, right? You have a set of reactants. You have to create a carbocation intermediate in the first step. And then that carbocation intermediate reacts with the nucleophile in a completely second step that is completely discrete from the first step. So that means you're going to have one mountain to get to your carbocation that will have one transition state. That's going to be the rate limiting step for this reaction because forming a carbocation is always going to be hard to do. But the benefit overall of this reaction is that that carbocation can then react with your nucleophile and give you a downhill reaction to get to your set of products that you are trying to get to. So the second step is a fast step with a low activation energy. And I've started here with a negatively charged nucleophile, which means I didn't need that third protonation inventory step. But if I did, we could actually add a third step to this energy diagram. So I'm out of time. I'm going to stop here, but just know that we will pick up where we left off with SN1 on Friday. We'll finish up SN1 and we'll go back to the beginning and talk about the one new-ish synthesis reaction for this chapter as well. I'm going to post all of the slides for SN1, SN2, and the comparison for the two. So if you guys want to get a little bit of a look ahead as to what's coming for part of Friday's lecture, I'm going to post all of these slides together today. And in the chat box, somebody's asked about Chapter 5 quiz. I will be releasing those today. I didn't want to release grades and have you guys distracted from class today. So I will be releasing those, and likewise on the slides, you'll be able to see how I calculated midterm grades. And your midterm grades did include your Chapter 5 quiz, which is quiz number 4. Okay, thank you guys, and I hope y'all have a nice day.